Ladies and gentlemen, I give you Alan Hájek.
So I'm delighted to be here for this wonderful occasion, honouring Bill. When Samantha Brennan was in Canberra about a year ago, she said there were some plans for this event, and I told her, I'm coming. Great to be here. I have two debts of gratitude to Bill, a personal debt and an intellectual debt. First, the personal debt. Picture me arriving here as a nervous MA student back in 1985, ill at ease, out of my comfort zone. My undergraduate degree was in mathematics and statistics. I had done zero philosophy. The only thing I knew about philosophy was the Monty Python song, which, by the way, stood me in good stead. In an early seminar, I remember someone said, that sounds like something Hume would say. I thought, David Hume could out-consume Wilhelm Friedrich. Okay, I know that. Anyway, I arrived here, I was uneasy, and Bill took me under his wing. He really looked out for me. In fact, he's still looking out for me, thanks to the phone call, the wake-up call this morning. Secondly, the intellectual debt of gratitude. Philosophers often imprint on their early philosophical influences, their early mentors. And so it was with me. My first ever philosophy seminar was with Bill. It was on scientific reasoning and Bayesianism. And it got me hooked. And he got me, in particular, interested in a problem involving near certainty and extreme improbability. And we eventually published a paper on that. And that concern with the improbable has informed much of my work since, stuff on conditional probability and independence and Pascals Wager, Hume on miracles, various things I'll tell you about in the course of this talk. So here I am all these years later, still fascinated by the improbable. The fascination began in those early days with Bill, so look what you've done, Bill. And anyway, in this talk I will invite you to join me and Bill in our fascination with the improbable. And I came in to change this. What's the trick?
So you want to use the mouse and click on your PowerPoint.
To the right, Harperfest.
A little more.
Movable disc.
And last one. Look, no, no, that one.
Yep. Hey.
And pressing F5.
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 Oh, sorry.
One help.
Yeah, actually, it's
On top, slideshow.
okay. Between us all. So I'm going to begin my case that we should really take the improbable seriously, my plea for the improbable, by looking at its work in science, in philosophy, and elsewhere. It's got a number of important applications. Starting with, this is familiar, from statistical methodology, significance testing. So, typically in classical statistics, pick a null hypothesis, H0, against an alternative hypothesis, H1. We reject H0 if by its lights the probability of the data that we've collected, at least as extreme as that observed, is too improbable, typically less than 0.05 or 0.01. These are the thresholds of incredibility. And this alerts us to a point that should be obvious. Improbable has to be relativized to a probability function. If you like, at the other end of the spectrum, as well as data fitting a given hypothesis too poorly, you can also fit it suspiciously well. Think of a famous case, Fisher accusing Mendel of having cooked the books in his pea experiment. The data fitted his theory of heredity a little too well, it seemed. And Fisher, doing a chi-square goodness of fit test, concluded the probability that by chance alone the data would fit his theory that well was about 3 in 100,000. Suspicious. Cournot is famous for this principle. An event of small probability singled out in advance will not happen. And Borel says the principle that an event with very small probability will not happen is the only law of chance. And various probabilists support Cournot's principle, and so does Glenn Schaefer nowadays. The principle still has some currency, and he's recently rehabilitated it. Maybe you know what's coming.
Very low probability.
Cheney said notoriously, if there's a 1% chance that Pakistani scientists are helping Al-Qaeda build or develop a nuclear weapon, we have to treat it as a certainty in terms of our response. The USA had to confront a new kind of threat, that of a low probability, high impact event. Now, Cheney doesn't say just quite how widely his 1% doctrine generalizes. Cournot didn't tell us just what the threshold of incredibility is, but it's clear that whatever intuitions they're appealing to, they're diametrically opposed. Cournot effectively rounding down an event's low probability, treating it as if it's 0. Cheney rounding it up, in this case, treating it as if it's 1. Let's turn to the improbable doing philosophical work. Improbable events are their key philosophy. Concern with them has driven philosophical positions and insights. Starting with the lottery paradox, which again Alan doesn't like that much. So, understood a certain way, the lottery paradox puts pressure either on the so-called Lockean thesis that rational binary belief corresponds to subjective probability above a threshold, maybe 95% or 99% counts as belief and everything above, or the closure of rational beliefs under conjunction. And for the thesis to have any plausibility, this putative threshold for belief must be high, like 99%. And accordingly, the probabilities involved in the lottery paradox will be small. The idea is you have a lottery with sufficiently many tickets. Each ticket's probability of winning is below, of losing is above the threshold for belief. So you believe of each ticket that it will lose, and yet you are certain that some ticket will win. Notice that lotteries cast doubt on Cournot's principle. Some ticket does win. And we see an interesting feature of small probabilities. They may accumulate, combining to yield large probabilities. Vogel gives the following argument for skepticism about knowledge. Oh, look, I know where my car is parked right now, it seems. Hang on. I don't know that I'm not one of those unlucky people whose car has been stolen during the last few hours. I know a bit about the crime statistics. I know there's some chance, it's small, but bigger than 0, that my car has been stolen. In which case it seems I don't, after all, know where my car is parked. Indeed, I don't even know if it's parked. Maybe it's being joy-ridden around the town. The improbable is the flip side of the probable. If P is probable, then not P is improbable. And the probable has done philosophical work, and they have a special place, especially probability 1 events have a special place in probability theory. I'm thinking, for a start, of the various classic limit theorems, so-called almost sure results. Various convergences occur with probability 1, not with certainty, but with probability 1, and that distinction will prove to be important again and again. And the probable doing philosophical work, think of the problem of old evidence. According to Bayesian confirmation theory, E confirms H according to probability function P. Just in case this inequality holds, E raises H's probability in this sense. But if P of E is 1, then these probabilities are equal, and E apparently has no confirmatory power, at least by these lights. And that seems wrong. Even when we're certain of the advance of the perihelion of Mercury, this fact seems to support general relativity. Okay. So this is just to warm you up in case you weren't already warned that the improbable is of interest to science, to everyday life, and to philosophy. But now I'm going to go on to make my own case for it, and I hope more strongly. So I've already pointed out many ways in which scientists and philosophers do care about the improbable, and this does much to build my case that they should care. Many of the examples are important and well motivated. We want a general philosophy of probability. We want a general probability theory that can handle these events. And as we will see, sometimes specific problems arise only in virtue of an event's extreme improbability. Probability interacts with other things that we care about. Something being improbable can matter to these other things. I'll give examples of that. And there are problems created by low probability events that are similarly created by higher probability events. But when they're improbable, we are liable to neglect them. So think again of skepticism about knowledge, as we saw. I mean, if car thefts were probable, it would just be obvious that I don't know where my car is. The problem was, it seems that you get the same undermining of knowledge even with low probability. That's Vogel's belief. But we're liable to forget about the low probability car thefts. And I'm going to make a related point about counterfactuals later on. All right, so far I've assumed you have a tacit understanding of what I'm talking about. Let me be a little bit more specific about what I mean by the improbable. So I'll count all of these things as improbable. Events that have probability 0 are always improbable. No apologies, they're just improbable. Events that have infinitesimal probability, and this distinction will matter later. So now I don't mean 0, I mean positive, but smaller than every positive real number. That improbable. Events that have small real value probability. So now there's nothing sort of fancy about the numbers. These are just good old positive real numbers. What do I mean by small? Well, obviously that's vague and context dependent, but we know clear cases when we see them, and my cases will be clear. You won't begrudge them, I'm sure. Finally, maybe this is a category you wouldn't have thought of. Events with imprecise probability with an improbable upper limit. So I'll be thinking now of interval valued probabilities where the top end is low in senses 1, 2, or 3. Okay, so as I said, there are various peculiar properties of low probabilities, and I want to use them to do some philosophical work. So I'm going to go through these properties systematically, showcasing each of them with a philosophical application, a philosophical payoff. Right, starting with probability 0. Much of what's philosophically interesting about probability 0 events derives from just weird facts about 0. 0 is the weirdest number of all, I think. And it's weird in completely familiar ways. You know, children in elementary school know these facts. I think each of these weirdnesses leads to a distinctive philosophical problem, as I will try to convince you. Now, and this is an issue that will come up more than once, we could reasonably dismiss probability 0 events as don't cares if we could be assured that all probability functions of interest assign 0 only to impossibilities. And in the jargon, these functions are so-called regular. That's a strikingly unmnemonic word for this property. Strictly coherent, again, doesn't quite convey what we're getting at. I'll use the term open-minded just to remind you the probability function is closed-minded only to genuine contradictions or impossibilities. To anything else, it's open-minded in the sense of at least bestowing a little bit of probability and maybe more than a little bit. I think open-mindedness is part of the folk concept of probability to the extent there is one. People say things like, if it can happen, then it has some chance of happening. I've done an empirical survey on open-mindedness. I asked two of my friends. I do think there is something in commonsensical thinking about probability that captures regularity, strict coherence, open-mindedness. And more interestingly, it has support from some weighty philosophical figures, for example, Lewis. We'll see how much havoc probability zero but possible events wreak. It would be nice to banish them. A lot of what's coming next will be just cases of the trouble you get into with these zero probabilities for things that can happen. It'd be nice if they aren't out there, but they are. There are apparently events that have probability zero, but that can happen in violation of open-mindedness. Now, there'll be different examples, differing degrees of controversy surrounding them, but let's make this one our sort of canonical case, and if you don't like this one, but you like another one, just substitute the one that you prefer. But let's fix our minds on this one. The fair coin is tossed infinitely many times. The probability that it lands heads every time, forever, is zero. Now that's clearly true if we're restricted to real values for probabilities. Later on we will lift that restriction. For now, keep it. The probability of each infinite sequence, not just that one, pick your favorite sequence, is zero. And again, just give me this for now. Later on we can revisit it. So let's see what trouble we can create using this sequence. Another case which will be useful later will be throwing a dart at the 0-1 interval, as philosophers of probability are fond of doing. Here's the interval, here comes the dart. Whoa. And making all the usual assumptions, you know, infinitely thin dart hits a point, uniform distribution over the interval, corresponding to the fairness of the throw, not favouring some part of the interval over some other. Various non-empty subsets get assigned probability 0, all the singletons, the finite subsets, all the countable subsets, and even various uncountable subsets like Cantor's so-called ternary set. All right, so there are various non-trivial and interesting examples of probability 0 events, and I say they create various philosophical problems, each associated with a peculiar property of the arithmetic of 0. So let's look at some of these peculiarities. Can't divide by 0, as any kid in elementary school can tell you, at a certain age. Now this creates problems for the canonical ratio analysis of conditional probability, as I like to call it. So the probability of A given B is this ratio of unconditional probabilities. Well, with the proviso that the bottom line better be positive. The trouble is, sometimes it's not. What's the probability that the coin lands heads on every toss, given that the coin lands heads on every toss in that infinite case? Now I say that intuition tells us, sorry Brian, I know you don't like the word, intuition, tells us, indeed it yells at us what the answer is. What's the answer? 1. 1, surely. But the ratio formula cannot deliver that result because the denominator is 0. The probability that the coin lands heads on every toss is 0. And there are less trivial examples. The probability that the coin lands heads every toss, given that it lands heads on the second, third, and fourth, so from then on, it seems to be a half. And again, the ratio formula cannot say this. Now these problems, we can quickly parlay into problems for conditionalization. That's obvious enough. Because conditionalization is defined in terms of the ratio formula, at least canonically. So just a reminder on conditionalization. if your initial probability function is the initial, you become certain of a piece of evidence or an E, you update, it says conditionalizing according to this formula. That is, your new probabilities are your old conditional probabilities given. And again, note the proviso. The initial probability of E had better be positive. All right, suppose you learn that the coin landed heads on every toss after the first. What should be your new probability that the coin landed heads on every toss? Half, surely, but that conditional probability is undefined, so conditionalization, so defined in terms of that ratio formula, cannot give you this advice. All right, obvious response, let's get more sophisticated. And there are more sophisticated methods for solving these problems. And in fact, Bill has written about this topic, and so have various authors, including myself. And, you know, pick your sophistication. You might appeal to primitive conditional probability functions. Again, something I learned from Bill, Popper functions. Kolmogorov had his own sophistication, thinking of conditional probability as a random variable, conditional on a singular algebra, appealing to the Radon-Nikodym theorem for the existence of this random variable. So there are things that can be done, but the point is something must be done, I say. We can't retain the Bayesian orthodoxy in the face of such cases. And when we look at these sophistications, well, we have to assess their costs. Okay, now, so far that's pretty familiar, I think. So now let me, I hope, get a bit less familiar. Here's another weirdness about zero. It's the multiplicative destroyer. Multiply anything by it and you get zero back. And I say this spells trouble for the usual definition of probabilistic independence. Okay, we try to capture the idea of A being probabilistically uninformative about B. And canonical account of this, A and B are said to be independent, just in case we have this factorization holding. The probability of the conjunction is the product of the individual probabilities. According to this account, anything with probability 0 is independent of itself. We just do the math. 0 equals 0 times 0. But surely identity is the ultimate case of probabilistic dependence of the kind that we're trying to analyze. This notion of informativeness. So, suppose you're wondering whether the coin landed heads on every toss. Maybe you've got some large bet hinging on the result, as you will later. And suppose I give you the following information. Oh, the coin landed heads on every toss. Do you think that's informative? I say nothing could be more informative than that. But according to this account of independence, the coin landing heads on every toss is independent of the coin landing heads on every toss. And more generally, according to this account, any proposition with probability 0 is probabilistically independent of anything. And this includes its negation, anything that entails it, anything that it entails. So I think this is even worse than the problem for the conditional probability ratio. That was guilty, you might say, of a sin of omission. There are cases in which I wanted it to speak and it was silent. Here, the account speaks and I wish it would shut up. I say it's guilty of a sin of commission. It's telling us that certain independence relations hold when they don't. There's another weirdness about 0. While it's the most potent of all numbers when it comes to multiplication, it's the most impotent when it comes to addition and subtraction. It's the additive identity. Adding it to any number makes no difference. And I say this creates problems for decision theory, again, understood in an orthodox way. So arguably the two most important foundations of that decision theory are the notion of expected utility and dominance reasoning. And these are familiar, quick reminder. Expected utility is a measure of choice-worthiness of an option. the weighted average of the utilities associated with that option in each possible state of the world, the weights given by corresponding probabilities, or if you like, conditional probabilities, that those states are realized. Weak dominance reasoning says that if one option is at least as good as another in every possible state, and strictly better in at least one possible state, then it's preferable, assuming independence of options and states. And yet probability zero propositions show that expected utility theory and dominance reasoning can give conflicting verdicts, at least when interpreted a certain way. So here's the trick. Suppose two options yield the same utility except on a proposition of probability zero, but if that proposition is true, option one is far superior to option two. So let's go back to our dreaded coin. You can choose between these two options. One, if it lands heads on every toss, you get $1 million, otherwise you get nothing. Option two, you get nothing. I hope you have a preference, because I do. Expected utility theory says that these options are equally good. They have the same expected utility, 0, 0. Dominance reasoning says that option one is strictly better than option two. It's preferable. Which is it to be? I say option one's better. I say dominance reasoning is getting this right. I say it's a counterexample world to expected utility theory as it's usually understood in terms of this figure of merit, expected utility, because the figures of merit are tied in this case. Now again, subtle issues here. There are lots of epicycles, and this is a 45-minute talk, which is already going to be 50 minutes. Now, a number of you may be thinking, he keeps on talking about these zeros. They're not really zeros, they're decimals. And you might appeal to, say, non-standard analysis, so-called hyperreals, which gives us a beautiful mathematical theory, including infinitesimals, numbers bigger than zero, smaller than every positive real. So we might say that the probability that the coin lands heads forever is not really zero, it's rather an infinitesimal. Lewis says zero chance is no chance. So notice we're going from a probabilistic fact to a modal claim. He means no chance in the sense of not possible. And nothing with zero chance ever happens. If you like, that's an extreme version of Cournot's principle, but this time it's a plausible one. Zero probability counting as small probability. But if something has infinitesimal chance, that's still some chance. And Brian advocates using infinitesimal probabilities. In Lewis's case, it's a sort of more widespread endorsement that any rational agent would start out with a regular, open-minded probability function. But in the cases considered, aren't the probabilities really zero, even when you allow the infinitesimals in? Now, this is something we could have a good debate about. We already have in the bar a couple of times. Williamson has an argument that the probability of heads forever really is zero, even allowing infinitesimals. And we could talk about that later if you want. And here's my argument. Even if you allow yourself a hyperreal valued probability function, now you help yourself to infinitesimals. So you've enriched the range of the probability function. I will now enrich the domain. I'll enrich omega and the sigma algebra from it in, say, my data throw. I'm going to now make the landing points the hyperreals, not just the reals as they were previously. So now I ask, what's the probability of a particular point? Let's call it x. So x is strictly contained within nested intervals of the form, epsilon on 2 either side, little infinitesimal intervals, and you can even imagine them shrinking down 2x. Okay? The probabilities of those intervals, assuming the flat distribution, will be the corresponding infinitesimals, will be epsilon for each of them. whatever epsilon is. The probability of the point is bounded above by all these epsilon, and thus must be smaller than all, which is to say 0. And here I really mean 0, and that's crucial. Anyway, we should judge our total theory, in this case our Bayesian epistemology and decision theory, by its virtues and vices. And we've seen what I take to be some serious vices of orthodox Bayesianism, or certainly with the real valued probabilities and the vanilla ratio formula for conditional probability and conditionalization defined in terms of the vanilla formula and independence as the product and decision theory understood as expected utility as previously we did. And not just Bayesianism, but probability theory, so understood. So one way or another, we need to go orthodox. And then we look at the costs and the benefits for which way we go. Okay. Now the probabilities will be quite straightforward. No weird 0 stuff, no weird infinitesimals, just familiar, real valued numbers with small ones. So nothing weird about their mathematics, but I say they give rise to a host of philosophical problems in their own right, real valued but small positive probabilities. I'm going to do the work. All right, so we come to the part of the talk. Given this is a whole book project that I have going. In fact, I have a whole manuscript. And I get really 2 reactions to it. Some people think I've lost my philosophical marbles. And other people are utterly convinced and say it's just obviously right. It's just game over. So I wonder which reaction you will have, or maybe something in between. Anyway, here's the argument. So stare in the face of chance. So just picture as vividly as you can what a chancy process is like, and for definiteness, let's make it the coin toss, coin in my pocket, being tossed, landing heads or tails. But I won't actually toss the coin. Let's just consider the counterfactual. If the coin were tossed, it would land heads. So I submit that's false. There's no particular way that this chancy process would turn out were it to be initiated. And I'll use the words of Dick Jeffrey. That's what chance is all about. To think that there's a fact of the matter of how the coin would land is to misunderstand chance. Well, so far you've probably assumed it was a fair coin. Let's now not assume it. It's a highly biased coin. Highly biased to heads, there's just a chance 0.0000001 of tails. And still I say, it's false that if the coin were tossed, it would land heads. It might not. It might land tails. Again, you can't second guess in this sense the outcome of a chancy process where the counterfactual is concerned. That's what chance is all about. Consider a fair lottery. If you were to play the lottery, you would lose. It's false no matter how many tickets there are in the lottery. And so it goes. Okay. Now, in an indeterministic world such as ours appears to be, lotteries, in a broad sense, abound. Here I'm thinking of quantum mechanics. And I don't just mean your canonical quantum mechanical examples of radioactive decay or spin measurements in a Stern-Gerlach apparatus. The indeterminism reaches medium-sized dry goods, oversized wet ones, just less obviously. So think, say, of a cue ball approaching an 8 ball. This might approximate a deterministic system, but even these balls are not immune to quantum mechanical effects. The first ball might spontaneously quantum tunnel to China or to the North Star. Or if I were to jump, I would come down. Well, hang on, there's some chance of my jump being ill-fated. I might vaporize mid-jump. Extremely improbable. of course, but bigger than 0. And I claim that's enough to undermine the counterfactual. So these seemingly deterministic events are actually subtly indeterministic, and then the previous argument about chance kicks in. They are in that sense like lotteries. Now again, subtle issues here. I've written a book about this, and you're hearing a 5-minute version of it. I know there are various contextualist moves and so on. That's anyway the quick version of the argument. Now there are various reasons why you may not be staring chance in the face. For example, you may be ignorant of these quantum mechanical facts. Or you may know about them, but they just may not be relevant to your current interests or to your current discussion. So you're just not thinking about them for some reason. Or maybe you're thinking about them, but for whatever reason just ignoring them. Just like maybe an annoying person talking to you, you can ignore them even though they're staring you in the face. The trouble is the chance is staring at you. So it doesn't care about your ignorance, it doesn't care about your ignorings. It's constantly there, I say, in the background, and as such undermines these ordinary counterfactuals. It's heedless of your ignorance, defiant of your ignorance. So once you take seriously what quantum mechanics says, you should see chanciness almost everywhere. And again, on certain interpretations of quantum mechanics are big issues, but just spot me that. The world looks like a huge collection of lotteries. But whether or not you take seriously what the theory says, that's apparently how the world is. Next kind of case. Multiplication by extremely large utilities. Even extremely small positive probabilities can be offset by multiplication by extremely large utilities when calculating expected utilities. And the most famous case of this, if you like, the original decision problem, Pascal's Wager. And I hope it's mostly familiar to you. Just to quickly recap the main bits. 2 ways the world could be: God exists, God does not exist. 2 things you could do, but think of this as a decision problem. Wager for God, wager against God. You might think of that as believe in God or not. This is Pascal's terminology. It's more try to cultivate belief in God. That's what wagering means. Let's look at the utilities. Infinity, that's what you get if you wager for God and God exists. Think of that as salvation, as Pascal put it, an infinity of infinitely happy lives. But in every other case, you get your earthly life, which is finite, and that's it. Some finite utility, and that's that. So let's call those values F1, F2, F3. The probability that God exists should be positive. It could be very small, this is crucial. It could be 1 in a million, or smaller, but positive. But still, you should wager for God because rationality requires you to maximize expected utility. And put those premises together, that's Pascal's conclusion. You should wager for God. Rationality requires it of you. And just in a little bit more detail, let's assume your positive probability is P for God's existence. Your expected utility of wagering for God, well, that's infinity times P, that's F1 times 1 minus P, and that's infinite. Your expected utility of wagering against God, some finite stuff plus some finite stuff. Infinity is greater than some finite value, so you should wager for God. So that's the famous wager. But I say this argument is invalid. To grant Pascal every premise, grant him exactly the decision matrix and the positive probability and the maximization of expected utility, doesn't follow that you should wager for God. specious steps to assume that only the strategy of wagering for God gets the infinite expected utility. But he's ignored all the mixed strategies. So consider this strategy. It's definitely not Pascalian. Toss a coin. Heads you believe, tails you don't. Heads you wager for God, tails you don't. What's its expected utility? With probability half, the coin lands heads. Now you're in the case where you're wagering for God, and by Pascal's lights you get infinite expectation. And with probability half you get something finite. So you have a 50-50 mixture of something infinite and something finite, which is infinite. So that mixed strategy is also infinite in expected utility. And once you see the trick, you can run it again and again. Believe in God just in case your lottery ticket wins next week. 1 in a million times infinity, still infinity. Believe in God just in case a meteor quantum tunnels its way through the side of this auditorium and comes out the other side before the end of this talk. 1 in a googolplex times infinity, still infinity, and so it goes. But that still understates Pascal's troubles, because it seems anything that an agent might choose to do, maybe a mixed strategy between wagering for and wagering against God for appropriate probability weights. But whatever one does, one should apparently assign some positive probability to winding up wagering for God. So suppose you don't want to think about all this wagering. You just want to have a beer. Still, there's some positive probability that while you're having the beer, you'll have an epiphany, you'll wager for God, and then the infinite expectation kicks in, and by Pascal's lights, the beer is really a mixed strategy and has infinite expectation. Now, I've made much of these points before. Now I just want to bring out another point. By open-mindedness, one has to assign positive probability to such non-Pascalian routes to wagering for God. It's a contingent matter whether I have an epiphany during the beer. So by open-mindedness, I must assign positive probability to it. And so it goes for whatever you do. And so by Pascal's lights, it seems that everyone enjoys maximal expected utility at all times. This is a novel proof of Leibniz's conventions, the best of all possible worlds. All right, so let me leave this with a dilemma. If a Pascalian agent is open-minded, all practical reasoning is useless. If not, the earlier theoretical problems, the conditional probability, conditionalization, independence, and decision theory, are alive and well, unless we do something. We have to fix them. Now the wager can apparently be rendered valid. These they sound valid. Replace that infinity for salvation with big F, some big finite value. Now this is not good Pascalian theology, but at least the argument will go through. As follows. Now the expected utility of wagering for God's finite, but now I'm imagining F is really big. Expected utility of wagering against God, some finite value. Well, how big is F? If it's large enough, you should wager for God, namely large enough to make the first expectation bigger than the second. And some real-world decision problems look rather like this because they involve sufficiently high stakes relative to the associated probabilities. This brings me to the last part. Okay, remember my four-way taxonomy? We're now in the final part of that. Imprecise probabilities with small upper limits. So sometimes our probabilities are imprecise due to lack of relevant information or conflicting information. Think of imprecise probabilities as interval value. X up to y. And y may be very small, and it will be in the cases I'm going to think about. but when the associated stakes are sufficiently high, they may still be cause for serious concern. So, very current example. In fact, how current is it? How's the volcano going lately?
Still a
Without
problem.
defining groups that I care about this.
Nothing found.
Okay.
But this morning you're talking about Spain having events.
Okay. Right.
So don't go to Spain.
Don't go to Spain. So remember, all of Europe's airports closed because of the risk to flights posed by the eruption of the volcano. And you had various officials saying the probability of crashes was small. Eyes lit up. And actually also imprecise. You know, they really didn't have much of a clue what the probability was. But the stakes were so high that it was wise to cancel the flights, and I could see that that was reasonable. Actually, also because of the accumulation point, because there were lots and lots of flights. Last example. Climate scientists differ in their probabilities of various scenarios of global warming. And look, I'm no expert on global warming. I can't do better than follow the scientists, but they're giving me conflicting things to follow. So let me give a particular reading of this graph, which is fair and it will make the point that I want. So on the horizontal axis, there are various scenarios of ever greater seriousness for net global warming. So read this as, say, a 2-degree Celsius net global warming over a period that's roughly 50 to 100 years, let's say by the end of the century. And now here are various scientists putting their PDFs over these scenarios. I want you to notice a couple of things. For a start, the modes are somewhere around here. So the scientists are pretty much agreeing. The most likely scenario is something like a 1 to 3 degree warming. And that's how the global warming discussion, the debate is usually framed. They say things like, very probably there will be roughly 2 degree warming in the next 50 years unless we change our ways. But I'm rather more worried about what I see up here. Tails. Actually, you can't see it very well. Again, there's a bit of a spread here, but even the lowest curve is giving some positive probability to the 10 degree scenario. About 1 in 100. Now, you could maybe try to dismiss the 2 degree scenario. So we mainly hear about the most likely scenarios, like the 2 degree scenario. And to be sure, serious consequences, but some people argue not catastrophic. You know, life would still go on recognizably as before. Pretty bad for the Maldives, but the world would continue as much as before. But maybe we should be more concerned with the much less likely scenarios, ones that involve truly catastrophic consequences. And this is so even when the corresponding probabilities are imprecise. So again, this is worrying enough. This is what, in a way, really worries me. Especially, you know, down here, this is 1 in 100 for something utterly devastating. I wouldn't fly if every 100th plane crashed. Fond as I am of travel. Okay, so it seems that we have to be worried about this low probability but high impact. This is high impact, if anything, this event with a probability, let's say here, at least 1 in 100. 1 in 100 is 1%. So even he should be worried. Thanks a lot.
You said all counterfactuals are false.
Most.
Most counterfactuals are false. counterfactuals of chance, consequences, fine.
Yep, fine. I like that. In fact, that's part of my my strategy of sort of explaining away our success with using counterfactuals. You know, it seems you might worry I'm proving too much. I mean, we seem to do so well with our counterfactual language, and here am I claiming most of them are false. So first point, I think falsehood gets a bad rap. I think you can do a lot of good stuff with falsehoods. In fact, I think a lot of science does exactly that. But second point, in the neighborhood of the false things that we actually say, I think are true counterfactuals. It's not what we said, but these are the probabilistically modified consequence. If I were to jump, I would fall. False. If I were to jump, I would fall with chance 0.999999996. Get the number right, and that I say is true. And you don't even have to get so fancy. Just if I were to jump, I would very probably fall. That's true. It's not what I originally said, so it's close enough to what I said that I can get away with it.
So, thank you. I found this a very interesting stimulating talk. There's a lot of things that I want to talk about, but let me just take a few right now. One is, there's a nice example of the sort of thing you're talking about at the end of claims that we disregard the low probability but extremely bad consequences. As you may know, there are people who conjecture that the LHC might create a black hole and stuff like that, because we're all like on Earth. And there was an article published that tried to estimate some parameters and calculate the probability of that, and it was something very reassuring and low. Adrian Kent wrote this response to that, saying, well, look, actually, if you're regarding this as reassuringly low, you're actually putting an absurdly low price on thinking legs, because you're not really, and he made some more estimate. I don't remember what the numbers were, but I need to find it in reference. But on a more substantial note, I agree entirely with one thing with Frank said, but one thing in particular, that if we're going to make a move to some kind of unorthodox probability theory, it's a cost benefit thing. And one of the issues, one of your things you dislike about the orthodox approach is the notion of independence being the probabilities factor, and you were worried about that breaking down and when the probability is zero, because surely any proposition is informative on itself. Are you also worried at the other end, where when the probability is one? Like, you know, I seem quite comfortable. I feel quite comfortable saying that the probability of A is one, and then B, no matter what it is, even if it's A, is irrelevant. Are you fine with that too?
Okay, and I'll go back to the previous question as well. Start with the second one.
Yeah.
Certainly more comfortable. Even there, I have the following slight discomfort. So consider the proposition that the coin will not land heads forever. Okay. So that's probability 1.
Right.
Suppose you now learn the coin landed, say, tails on the first toss. I think that is informative regarding that proposition, because in a technical sense it was an open question at the outset whether the coin would not land heads forever, and the first tail closed the question. So in that sense it was very slightly informative.
I worry if we're just conflating two notions of dependence. One, a probabilistic notion, which is actually captured just fine by the actual condition, and then but I think it's important not to conflate that with logical relations, because surely no proposition is logically independent of itself.
Although, well, it's not just logical. So, for example, if you have a lot of money resting on this bet, as I did, because remember I was going to offer you $1 million. In a way, I'd go, phew, the coin came in tails. in that sense, I think it is informative regarding the proposition that we were betting on. Minimally so, but still informative. But you might say, look, we are just capturing probabilistic informativeness, where I really mean changing a probability, and I agree the probability did not change. It went from 1 to 1. So it is the zero case that I care rather more about. And that really does strike me as serious. The zeros really turning into a 1. Nothing could be more important. Okay, and just regarding the first point, and I'd like to get the reference. Yeah, it's a little bit of a dilemma, how are we to treat the value of human life? If you treat it finitely, the loss of a human life is just some finite utility, well, it seems to somehow undervaluing the importance of life. But you see what happens if we give it infinity. You get the Pascals Wager problem. So, never mind foregoing something that might increase the probability of terminating someone's life. Just have a beer. There's some probability that someone will die as a result of that. And then that Pascalian worry kicks in. So it's sort of tricky either way.
So this is like a follow-up on the independence thing. Yeah. So, given your sort of overall approach, I'm a little bit puzzled by one aspect of that, right? So let's say that I'm on board with your point about conditional probabilities, and I say, yeah, there ought to be a way to talk about conditional probabilities when the condition is probability zero. Okay, there's various ways to this. All right, now. Your criticism of the independence was, well, we have this intuitive idea that what independence means is, not conveying any information about the thing. Now, of course, in the ordinary case, when we've got some proposition C which has positive probability, we can do that two different ways. We can do it the probability of the conjunction equals the probability, or we can do it with the conditional probability of the one thing on the other. It's the same. Right. Now, I guess my question is, why isn't it the right thing to say there that those two tests for informativeness just come apart there, and it's the conditional probability test that gets the...
Okay. So I think exactly that. So I don't think there's any tension in my views, because that's exactly what I think. Except you said use the conditional probability test. Which one? So one test would be X and Y are independent just in case P of X given Y equals P of X.
Right, that's one, yes.
Different one. P of X given Y equals P of X given not Y. Okay. And we could reverse them, and we could change the consequent, the condition in the test. So there'll be multiple senses of independence. Now these will all collapse in the orthodox theory. What's very interesting is, say, when you go to proper functions, now the distinctions matter. When you say that X and Y are independent, you have to say in which sense, because you won't get the entailments between these different senses. So suddenly independence becomes this much more complicated, said more positively, this richer thing. That's the view. That's what I think.
I am interested in why you think the infinite coin toss has the probability that you assign as. I mean, so it depends, of course, on what possible, what you think is possible. Right? So it might be the case that I've got this infinite string of coin flips, and each one can be either heads or tails. But it might be that my physical coin has the property that after some very large number n of flips, it just starts always flipping heads after that. Right? And if that happened to be the case, then it would be a finite probability that I get all heads, right? So there's an assumption about what's possible in an infinite coin toss game that guarantees that you have probabilities zero in this case. And we really have no experience with infinite sequences of coin tosses that would allow us to say something like that. So can you say a little bit more about how you come to the zero probabilities.
Oh yeah, so I assume just the consistency of IID trials. So constancy of probability across the trials. So that rules out the case.
But right, but so of course we don't really have evidence for that in an infinite case. It could be a very large number n beyond which the coin just starts always flipping heads, right? And no frequentist interpretation of probability based on finite experiences can actually guarantee one way or the other.
In fact, more than that, we've got experience that the coin will eventually disintegrate.
For example,
it won't be around anyway. So obviously this is an idealization. So I'm imagining this sort of ideal coin whose probability does remain fixed, the trial's independent. And I'm not pretending this is a real world coin, but as I said on one of the slides, I want a fully general probability theory. It does seem coherent to think about some cases. I'm reminded a little bit of John's talk yesterday and the super tasks and so on, that you don't literally have these super tasks, but they seem coherent. It'd be nice to have a theory that covers them as well. So I want my theory to do it. Brian.
I have to say something to that.
Okay.
So you're talking about going beyond the orthodoxy.
Mm-hmm.
The orthodoxy is Komagora. It's not just finite probability and so on. So,
yeah.
I mean, probability conditional on the sigma algebra is part of the orthodoxy. Right? And then there are various developments that take it a little further than regular conditional probability. So on. So I think it's a question as to whether that orthodoxy, right, which is when you really study probability to get to that orthodoxy, that's what people really use, is adequate, or whether it needs to be modified.
That's right. So for start, just answering the question about the coin, I want my orthodoxy, I want my theory to cover even these highly idealized cases. So,
I agree with that.
So that part was fine. And now I go to the high octane Kolmogorov sophisticated version, conditional probabilities of random variable. There are still problems there. I just had this teaser at one point. Well, we need to look at the costs and the benefits of the account. Teddy and his collaborators have various worries about even that sophisticated formulation. It seems you have cases where the probability of x given x is 0 almost everywhere against that loud intuition that I have that such a conditional probability should be 1. In fact, I would have thought that is the most fundamental intuition that can be had. It's like x entails itself. So even going to the full strength Kolmogorov theory, there are some worries. Worries about counterrelativity, De Finetti style worries. I also worry about, could have given a different talk, not about the improbable in the sense of probability 0 or low, the non-probable, things that just don't have a probability, like say non-measurable sets. Okay? And I still think certain conditional probabilities should be defined even for them. The probability that the dart lands in a particular non-measurable set, given that it lands in that set, I would say should be 1. So these probability gaps are going to be trouble for even the sophisticated Kolmogorov account. So again, I think you need more apparatus.
We should talk about how Kolmogorov handled some of these things.
Even the gaps?
Because probability is something conditional on sigma algebra. Depends what the sigma algebra is.
Yeah, that's true.
And you want some things, right? So you talk about the dart hitting the interval, and you want the probability that it's at that point conditional, but it hit that point to be 1.
Yeah.
Well, relative to the sigma algebra, the whole probability space, you started out with, you could certainly have all of those things. I mean, the examples that Teddy and these guys are trying to really find, they have
How about non-measurable sets?
Well, depends what you're going to do with it. If you insist on putting a measure on non-measurable sets, then you have to go to find an activity or something. Or get rid of them by doing measure algebras and throwing stuff out of your space.
Which the test ones. Let's see what we do. Yeah. Again, area fraught with controversy, but some people think there are more mundane examples of these probability gaps. Some people think, this sort of came up a bit in Jim's, well, related to Jim's talk this morning, about your own deliberations, your own free choices. So I don't subscribe to the following, but people like Levi and Gilboa and Schroen do. It's kind of, while you're deliberating, you can't assign a probability to your own decision. But offhand, I would thought even they should be able to say, I can assign conditional probabilities. The probability that I have a beer, given that I have a beer, is 1, even though I'm deliberating about whether to have a beer. So I think we want these conditional probabilities even when there are gaps.
An incredibly patient perspective.
Thank you. I just have a question about Pascal's Wager. If you could ascribe to F2, which is the utility if God exists and you wager against him, if you could ascribe negative infinity to that utility. And in so doing, thinking about mixed strategies in that sense, that really any sort of strategy would lead to wagering against God unless it would, as you're saying, it would be sort of the worst of all possible worlds. And I wonder if, in a sense, that kind of thinking of negative infinity at F2, in some sense, breaks down kind of an analysis of thinking about wagering in terms of mixed strategies.
Good. So read the paper that is coming out shortly that I've written on exactly this. So, in fact, some people interpret Pascal himself as already meaning this. You know, hell is infinitely awful damnation, so that should be a minus infinity. Yeah, I think that's not in the text, but it's certainly worth entertaining. And so then the mixed strategies have this indeterminate form, you know, infinity minus infinity, which is just undefined. And then you might say, well, salvation's better than that. Better infinity than undefined. And in that sense, maybe it's a cheap sense, but in that sense you might say outright wagering for God is better than the mixed strategies. I'd rather have this pure infinity than something undefined.
All right, well, let's thank Alan again.